Let's look at this function, and first we'll consider the function geometrically. Algebraically, the function is very complicated, and if I give you the actual definition, it would look like basically nothing. But there is a really deep geometric meaning attached to the determinant, and let's first look at this, and then go back to the algebraic definition. So let's start with the simplest kind of matrices. Let's take a matrix A, that is a 1 by 1 matrix given by a single entry. So for example, we could take A to be the number 2. And you can think again as a 1 by 1 matrix to be a real number. And let's consider now the real line. We can act on the real line by the number 2. And this is the first time when we look at a matrix not just as an inert block of numbers, but also as a function. So consider the matrix A now as a function from the real numbers to the real numbers. And the action is actually quite simple. Take a real number, multiply it by the entry of the matrix, so send x with 2x. And now you have the matrix where the single entry is 2 as a function from the real numbers to the real numbers. Take a real number, multiply by 2 that real number. The question is now, what is the geometry behind this action? Well, consider the real line, and consider part of it, the interval from 0 to 1. The length is 1, and now a usual notation for matrices, instead of using f for function, we'll use uppercase T for transformation. But a transformation is the same as a function, so we write T of A, so the function attached to the matrix A given by multiplication. And well, what's the action? We multiply every real number x by 2. Well, what happens? Specifically to the interval 0, 1. Well, if you multiply everything by 2 in this interval, it becomes the interval 0, 2. So now the interval is twice as long. And that's the geometry of the matrix 2. If you multiply real numbers by 2, well, what's changed is everything is twice as long. And so in this case, the determinant of the matrix 2 is simply 2. So the determinant of A is just the single entry if A is a 1 by 1 matrix. What if the entry was negative? So what if we have a second example where now A is given by, say, the single entry negative 3. Once again, we can multiply now not x by 2 but by negative 3. So we have another function on the real numbers. And let's see if there's something interesting going on here. So take the real line, consider the interval from 0 to 1, and multiply everything by A. Again, it is a 1 by 1 matrix. You can think of it as a real number. So multiply the real line by negative 3. Well, what happens to the interval 0, 1? It will become the interval negative 3, 0. So what's happened here? If you look at this, two things have happened. The interval from 0 to 1 is now 3 times longer, but a reflection took place, right? It was going from 0 to 1, now it's going from 0 to negative 3. So we do not want to kill the negative sign, because it gives you an additional piece of information. So the determinant of the matrix negative 3 is just negative 3. The determinant of A, therefore, is negative 3. And that's the case for a 1 by 1 matrix. The determinant is simply the entry of that matrix. In absolute value, it tells you by how much you're stretching or compressing length, right? If the number here would have been 1/2, then you would have went from 0 to 1 to 0 to 1/2. And the length would have been shrunk by a factor of 2. If the number is negative, you have one additional piece of information. Given that here the determinant was negative 3, well, everything is 3 times longer, but there has been a reflection about the point x equals 0. That's a determinant for a 1 by 1 matrix. So in general, for 1 by 1 matrices, the determinant of such a matrix, again we have a single entry, is just the entry of the matrix. Now you say, well, what about 2 by 2 matrices? So a 1 by 1 matrix is a function on the real line. Well, a 2 by 2 matrix will naturally be a function on the xy plane, right? So before we move on, we have to make one simple observation. Normally, when you look at R2, the points in the xy plane, you're used to writing R2 in the following way. xy, where x and y are arbitrary real numbers. That gives you the xy plane. Now, for us, since we want to multiply our points, right, that's the action of the matrix, we take a point and multiply it by the matrix. And so the question is, well, if we have a 2 by 2 matrix, say A, and you can think of this as a 1 by 2 matrix, then multiplication is not defined. It doesn't work. Well, the idea is, what if we flip this on its side? Instead of thinking of R2 as a tuple of real numbers, what if we put this tuple vertically? What if we think of R2 as the set of all 2 by 1 matrices? Geometrically, this changes nothing, right? The first entry of your column is the x component of your point. The second entry is the y component. Now, the question is, algebraically, does this make sense? Well, if A is a 2 by 2 matrix, and we try to multiply a point by A, this is now a 2 by 1 column matrix. 2 equals 2. So multiplication is now defined. And the new matrix will be also a 2 by 1. Another column matrix with 2 entries. Therefore, another point in the xy plane. And this is why, in this course, we will always write R2 as no longer the set of tuples of real numbers, but as the set of column matrices of length 2. Because geometrically, this changes nothing. Algebraically, multiplication by a 2 by 2 matrix on the point now works, right? And now you have its function. Give me a point in the xy plane as a column matrix, multiply that point by A, and you have a new point in the xy plane. And that is giving us a function from R2 to R2 by multiplying every point of the plane by the matrix A. So here's where we're at. So our matrix, say, is given by A, B, C, D, is a 2 by 2 matrix, and this is a function now from R2, the xy plane, to the xy plane. And as we've said, the action is quite simple. We take a point in the xy plane, and we send it to the new point A times the point xy. So take every point in the xy plane, multiply those points by A, and you'll have a transformation of the xy plane. We can compute the image, right? Because A, say, is A, B, C, D, times the point xy, and we'll have our new point. The x-coordinate will be ax plus by, and the y-coordinate, the second entry, will be cx plus dy. And now we have a function from the xy plane to the xy plane. And again, we can ask, well, geometrically, what is happening, right? So we take a point in the xy plane, multiply that point by A, and we have a new point in the xy plane. So let's draw a picture to figure out geometrically what's happening. Suppose we take the unit square in the xy plane. So the point 0, 0, This is the x-axis, the y-axis. We have the origin, the point 0, 0. This is the point x equals 1, y equals 0. This one is the point, let me just make these a little bolder. This one is the point x equals 0, y equals 1. And our fourth and final vertex is the point x equals 1, y equals 1. So the question would be now, what if we multiply every point inside the unit square by the matrix A? And that's what this notation means, right? If we go back here, we could have written, instead of writing this, we could have simply said, well, our function is t of A, the transformation induced by A, and how do we transform a point in the xy plane? Well, simply, we multiply the point by the matrix A. So now we're saying, well, let's do this. Let's multiply every point of the unit square by the matrix A. And we'll have a new object. Now, something we'll prove later on is that if you multiply the points on a line by matrix, the image will also be a line. So let's multiply this point by A. So x and y are both 0. Look at the end result. Replace x and y by 0. You get the point 0, 0. So the origin is sent to the origin. That doesn't move. Look at the point 1, 0. If you multiply this point 1, 0 by A, so here x is 1, y is 0. So both of these go away and you're left with A times 1, C times 1. So it's just the point AC. So suppose this is A, and just for argument's sake here, we'll assume that all A, B, C, D are positive real numbers. So the point 1, 0 becomes the point A, C. What about the point 0, 1? Well, multiply 0, 1 by A, so x is 0, so these go away, y is 1, so you get the point BD. And just for argument's sake, we'll assume that B is a little less than A. Suppose that we get here B, and D, say, is larger than C. So we had the point 1, 0 was sent to AC, so it's this point now. And the point 0, 1, when x is 0, is sent to BD, this point. And the fourth and final point is 1, 1, and if x is 1 and y is 1, you get the point A plus B, C plus D. But if you notice, there's something interesting about this. If you add B plus A, this would be the coordinate of your x component, and if you add D and C, your y component is the sum of these 2 points. So what you're going to have is a parallelogram. So this is the point, the image of the point 1, 1. So A times 1, 1 again will give you A plus B for the x component, and will give you C plus D for the y component. And you see the point, if you add AC to BD, you get the point with coordinates A plus B for x, C plus D for y. Right? Let's just verify this. So this point is a C plus this vertex, which is BD. And if we add these two, we get A plus B as the x component, check, and we get C plus D for the y component, check. So you see, if you add to this point, you get the fourth and final vertex. So the image of a square is a parallelogram. And now we can ask, okay, well, geometrically, how has the area been affected? From here to the area of the unit square, and here we know the area equals 1. The question now is, what's the area of the image of the unit square under multiplying every point of the square by the matrix A? Let's try to find the area of our parallelogram. And the idea is to actually be clever about this. Let's add too much and then subtract what we don't want. So you can embed this parallelogram into a larger rectangle. Namely, the rectangle whose length is a plus b and whose height is c plus d. So let's add now the entire area of the rectangle. We'll have a plus b, the length, times the height, c plus d. And now we want to remove what we don't want. And of course, we'll be left with the area of the parallelogram. So minus. If you notice, we can break these up into 3 subregions, right? We have this triangle here, a rectangle here, and a triangle here. And notice that they are right-angled triangles. So let's remove the area of the first. The length is a, the height is c. So the area is base times height over 2. That's AC over 2. So we have removed the area of this triangle. What's the area of the rectangle now? Well, the point here is a, the point here is a plus b, so the length is b, times the height is c. So the length here is b times c, so we get minus bc. Now we've removed the area of this. Finally, the second triangle here, well again the base is b, so minus b, the base. Now the height, we go from c to c plus d, so the height of our triangle here is d, so minus bd, base times the height, over 2. But if you notice, now that removes this area here, we have perfect symmetry from here, these 3 regions, to these 3 regions. This was BC, and look at this one. This is also B, and the height here is C plus D minus D, BC. So the area of these two are the same. And the same can be said with these two, right? This was base B, height D. Well, again, this is base B, height D. And finally, the area of these two are the same. The length of the base here is from B to A plus B is A. The height is C plus D minus DC, so that's AC over 2, AC over 2. So if we remove twice of that, we'll have removed everything that we don't want. So just multiply each term by 2. And now you've removed from the area of the rectangle everything that you don't want. So of course the leftover will be the area of the parallelogram. Let's simplify and see what comes out. If we expand, we'll have AC plus AD plus BC plus BD minus, well, 2 over 2 will give you minus AC, minus 2BC stays minus 2BC, minus 2 over 2 cancels BD. So what are we left with? Well, AC minus AC cancels, BD minus BD cancels, and we're left with AD minus 2BC plus BC minus BC. So you see the area was 1 of the unit square, and now the area of the parallelogram is AD minus BC. Now it is worth mentioning here that this number could be negative. The nice thing is, suppose this number was negative 4. If it were negative 4, 2 things would have happened. The area of this would be 4 times the area of this, so the area here would be 4, and if there is a negative, that means that a reflection would have taken place. So now we have the determinant of a 2 by 2 matrix. The determinant of a 2 by 2 matrix given by A, B, C, D is given by, and if you notice here, it's A times D minus these two BC. So it's AD minus BC. And now we have the determinant of a 2 by 2 matrix. The determinant of ABCD is AD minus BC. And again, we do not want to put an absolute value here, because if the determinant is negative, that implies a reflection took place. Let's look at one last picture that will summarize, for 2 by 2 matrices, the geometric nature of the determinant. We gave an example with a unit square, and the image was a parallelogram. The beauty of this is it works for any other type of region. So suppose that I have A being by a 2 by 2 matrix ABCD. And again, we have just derived the determinant of this matrix, ABCD, is given by AD minus BC. We also sometimes will rewrite the determinant. Instead of using square brackets around the matrix, we'll use large vertical bars without square brackets. And if we write this, this means the determinant of the matrix ABCD. It's another way of writing it. So suppose I give you a region in the xy plane, any region, and I call this R. And I say now, because A is a 2 by 2 matrix, I can multiply every point inside the region by the matrix A. And this will give me a new region, right? The transformation is simply multiply every point by A, and then you'll get a new region in the xy plane. Could be larger, could be smaller. And that's the image of A, the image of R, sorry, under A. And you might ask, well, okay, what if I know the area of R? And you multiply every point in this region by A, you have a new region. And you might ask, well, if I know the area of this region, what's the area of this region? And the answer is remarkably simple. The area of the image of R under multiplying every point by A is simply an absolute value, the determinant of A, times the area of the original region. And that's the determinant geometrically. If, say, the determinant of this matrix was 1/3, then the region here would be 3 times smaller than this one, so the area of this region would be 1/3 of the area of the original region. And if it was not 1/3 but negative 1/3 on top of it, there would have been a reflection from here to here. And that is the geometric nature of the determinant. And you could have done the same thing with a solid. With a 3 by 3 matrix, you would be acting on the three-dimensional space. So now you'd have x, y, z coordinates. And you could take a solid, call it S, and you can multiply every point of the solid by your now 3 by 3 matrix, and you would obtain a new solid. And you can ask a similar question. So here we said this is the image of S under A. And you can say, well, what if I know the volume of this solid? What is the volume of this one? Well, the answer is the same as before. So volume of the image of S under A is going to be simply equal to the absolute value of the determinant of the matrix A times the volume of the original solid. And that's the beauty of the determinant. It gives you the scaling factor for area if the matrix is a 2 by 2 matrix. If it is a 3 by 3 matrix, it gives you the scaling factor for volume. So the volume of the new solid is an absolute value, the determinant of the matrix, times the volume of the original solid. If the value here was, let's say, -4, this solid would be 4 times bigger than this one, and on top of it, because of the negative sign, a reflection would have taken place. And that is the determinant geometrically. The question is now, how do we go to figuring out algebraically the determinant for a 3 by 3 matrix, or a 4 by 4, or 5 by 5, and so on? And this will be our next video on how to extend the fact that for a 2 by 2 matrix, the determinant is simply AD minus BC. Can we then build from this to figuring out the determinant for a 3 by 3 matrix, or 4 by 4 matrix, or bigger?